Hey, PSY230 students. This is the Muddy Points review for week 7. So this week we're focused on the correlation. So one of the things to just sort of put us in context when we're talking about the correlation is that this is a shift for us because in a correlation, we don't have any independent or quasi-independent variables. So if we think about an independent or quasi-independent variable, this is the variable that created our groups in our research studies. So early on when we were doing the z-score and the single sample t, we just had one group of people. That was, they all got a treatment, let's say. So that was one condition, and that was our independent or potentially quasi-independent variable. The difference between independent and quasi-independent variable is that a true independent variable, the researcher selects and manipulates which condition participants are put in. Whereas in a quasi-independent variable, people are already in groups and the researcher didn't manipulate, didn't decide that. So for example, in most people's research projects, if like they're using gender as their grouping or groups in their study, those categories, male and female, are quasi-independent variable. So it's gender is the quasi-independent variable because being male or female, you were already that before you started the study. So the researcher wasn't manipulating and deciding, okay, you guys are males and then you guys are going to be females. They already are males or females. So, but this is going to be the first time with our statistics that we're going to have no independent or quasi-independent variable. So again, we used to have maybe one group and then we started to do two groups with our independent and dependent t statistics, two groups of scores with a dependent, two groups of people with an independent, and then we had three or more groups. So all of those studies had an independent or quasi-independent variable. For correlation, however, there are no independent variables. You are ultimately going to end up having two dependent variables. So if we remember what our dependent variable is, it's when we're measuring our participants. So we're not going to measure just one thing now. We used to do that, and that was our x variable. So whatever we were measuring, memory maybe, that would be our x. But with a correlation, we're going to be measuring at least two things. And for our purposes, we're going to be measuring two things. And what we're going to try to look at is there a relationship between those two things, but they're both dependent variables. So that's kind of a shift. And then that also leads us to having not only just an x variable, but now we're going to have an x variable and a y variable. So that's kind of a conceptual shift. I will say the correlation is probably the most popular and statistic out there. I'm pretty much able to look in just about any empirical research article and probably be able to find a correlation being reported somewhere. And that's partly because it's just used in all sorts of different ways. But let's go ahead and get to your questions here. So the first couple here is just the calculations themselves. The muddiest thing was calculating the R. I forgot that we have to use the square root in the denominator and then the other person's Pearson correlation calculations. So I'm just going to walk you through an example here, very similar to something I might do in the calculation videos, except I'm not going to do all of it. But so let's say we've got this research study where we have 4 participants. This will just make it a quicker calculation. So we've got 4 participants, and what we've measured is their age as well as the number of mistakes they make. So this might be a task, because one of the things we know in developmental psychology is that as we age, there's certain types of mistakes that we tended to make when we're younger that as our brain develops, we no longer make. So, as we move from infancy, we understand that objects have permanence, meaning that if I show you this pen and then I hide it from you, the pen is still there, but an infant wouldn't know that. So we developed that. So if I was doing object permanence tasks, the younger infants would make more mistakes and then the older children would make fewer mistakes. Or we might do conservation tasks. So like conservation of mass and conservation of volume. So let's say I had a glass here and it was full of water, and I say, watch this, and then I pour it into a very long, tall tube, and I pour the water in there, and now it fills up that, and I would ask which of these had more water in it. And younger children don't understand that however much water there was in here and when I poured it into the other one, it didn't change. It's the same amount of volume. So they understand that we conserve volume. But younger kids don't understand that. Their concepts around more are kind of superficial. So the two glasses essentially one will look taller and longer, and that seems like more. So they will actually say that has more water. So that would be a mistake. So what we're looking here then is just a relationship between these two variables. So we're doing some kind of, maybe it's a conservation task, and we're testing them a bunch of times and we're counting how many mistakes they make. And so we have their age and mistakes. And so what we want to see now is there a correlation between somebody's age and the number of mistakes that they make in a conservation task? Okay, so to then calculate this, what we want to do is ultimately calculate three things to start. And they're all essentially like a sum of squares. So we're going to be measuring some form of variability. So ultimately what we're going to end up doing is we're going to measure sum of squares x. We're going to measure sum of squares y. And we're going to measure sum of products. Okay, so those are the three things that we need to ultimately calculate our correlation. So our correlation is an R, and R is equal to the sum of products over the square root of sum of squares x times sum of squares y. This is that R is our final calculation. That's when we calculate our correlation. It's a correlation coefficient. But you'll notice that formula has three parts to it. It's got a sum of products, sum of squares x, and sum of squares y. So we need those formulas. So sum of squares x is one we've done before. It is just sum of x squared minus sum of x squared over n. Sum of squares y, technically we've already done something. It looks just like the one above, except replace all the x's with y's. So it's sum of y squared minus sum of y parentheses squared over n. And then sum of products is our new one. And so you'll want to watch the lecture videos on that. But the formula we're going to use, and the one that I'm going to suggest that you use, is sum of x, y minus, and then sum of x times sum of y over n. And I'm going to put parentheses around those so it makes it a little bit easier to see. All right, so these are our formulas. So we just calculate those three things, and then ultimately we're going to put it in to that calculation. So what we ultimately end up needing are 5 things from our table. All right, so if we think about this first, this age variable, we can think of this as our x variable. So I'm going to put an x above it. And we'll think of our second measurement as our y variable. So I'll put a y above it. So if I add these scores here, 5 plus 10 plus 6 plus 9, technically that is a sum of x. All right, and so that's 15 plus 15, or 30. If I add the mistake scores, 10 plus 1 plus 8 is 19, plus 3 is 22, that technically is a sum of y. Okay, so I could start plugging the sum of x and sum of y into my calculations. So here's my sum of x, there's my sum of y, and then I can again redo them here, sum of x times sum of y. Okay, so that would be the 30 and the 22. Now what I'm going to add is I'm going to do an x squared column. And that's where I'm going to square each of the x's here. So 5 squared is 25, 10 squared is 100, 6 squared is 36, 9 squared is 81. All right, so when I add that up, that is a sum of x squared. Let's pull up a calculator here. So 25 plus 100 plus 36 plus 81 equals 242. Okay, so now I've got my sum of x and my sum of x squared. I'm going to now do the same thing for the y. I'm going to create a y squared column. So y squared is 10 squared, which is 100. 1 squared is 1, 8 squared is 64, and 3 squared is 9. And then I'm going to add that up, and that's 9 plus 1 is 10, plus 64 is 74, plus 100 is 174. And then I have my sum of y squared. The last thing I want to do then is create an x times y column. And in my x times y, I'm going to take the original scores of age and mistakes and multiply them. 5 times 10 is 50. 10 times 1 is 10. 6 times 8 is 48. And 9 times 3 is 27. So now if I add those up, so we've got 50 plus 10 plus 48 plus 27 equals 135. And that is technically a sum of x, y, and it was 135. Okay. All right. So now what I can do is I can do all of my calculations now, because I have all of the components. You want to think about is I've got 5 things down here in my bottom of my table, and they just need to be plugged into my formulas here on the right. Okay, so I need my sum of x squared. There it is, 242. Minus, I need my sum of x, which is 30. Put parentheses around that and square it, and then divide by my n. Now my n is just the number of people in my study. So there were 4 people. They were measured twice, so I have 8 total scores that I started with, but there were only 4 people, so that's n. N is our sample size. So we have 4 people, so that's divided by 4. Okay, so this will then end up being 242 minus, so 30 squared is 900 divided by 4. Let's pull my calculator back up. 900 divided by 4 is 225. Okay, so let me move this out of the way here. So it's supposed to say 225, but let me make some room here. There we go. Okay, 242 minus 225 gives me a sum of squares x of, I'm just going to do it up here, minus 242, and then it'll just be the inverse, so 17, so it's positive 17. Okay, so that's my sum of squares x. So now if I want, I can start building my r calculation down here, and I just figured out the sum of squares x is 17. So I'm going to put that down there inside the square root. Okay, now I'm going to jump to the sum of squares y. So now I need sum of y squared, which is the 174 here, minus my sum of y, which is 22. Put parentheses around it, square it, and divide by n, which again is 4. So 22 squared divided by 4 is 121. So this will be 174 minus 121. And let's do minus 174. Gives me 53. Let's circle these just so they're a little more obvious. Okay. So now I know that this is going to be 53 down here in the bottom of my correlation calculation. Now the last one is I need to do my sum of products. So I need my sum of x times y, which is the 135, minus sum of x, which is the 30, times sum of y, which is 22, and divide by n of 4. So 30 times 22 is 660 over 4, and that divided by 4 is 165. And when I divide that, I get a negative 30. Okay. So that goes in the top of my correlation. So now I've got everything I need for my correlation. Negative 30 divided by the square root of 17 times 53. So let's multiply 17 times 53. 17 times 53 equals 901. So this is negative 30 over 901. Take the square root of that. And the square root of 901 is 30.01. And we'll 02. Okay. Now, if we run this through and just divide, so now we're going to save that and then take 30 and divide by it. That one. We get a correlation of 0.999. Which is, and it's a negative 0.999 because that should have been technically negative 30 divided by that. And so you always want to make sure you keep those signs here. So once the sum of product is negative, you're going to have a negative correlation. So that's a really high correlation. So it might be, I just made up this data. I might have created some data that is perfectly on a straight line. So I want to run this data through Jamovi and see if I made a mistake, because it's possible. It's certainly always possible. Okay, so let's enter our data. So we're going to make the age variable, and then column B will make our mistakes variable. Okay, so now my ages, I had 5, 10, 6, and 9. And then under mistakes, I had 10, 1, 8, 3. Okay, so now I've got my variables. So I'm going to run what's be under regression. It's just a correlation. So I'm going to run a correlation between these two. So it's just essentially I drag both over. So age and mistakes get moved over here. And there we get it, correlation of negative 0.999. So I did accidentally create an almost perfectly on a line correlation. So I can show you the, let's see. Don't want that. I want the, oh, it is. Yeah, there it is. So there's the data. Like it's almost exactly perfectly on a line. So that was kind of unintentional, but that is, yeah, that happened. So essentially what that's saying here, so if we go back to our result here, we have a correlation of negative 0.999. Again, correlations range from -1 to +1. So this couldn't have almost not been any stronger of a correlation. It is almost a perfect correlation. If it was a -1, it would be a perfect correlation. Positive ones are also perfect correlations. So this is almost a perfect negative correlation. What that means is that age and mistake are almost perfectly negatively correlated. That means that the as age goes up, mistakes go down, almost like by a unit. And so one of the things I'll also show you here is that the p-value here is less than 0.01. Or less than 0.1, which is just, again, it's a very unlikely result to happen by chance. Okay, so that is how we do the calculation for a correlation. Now, the next question, because I want to do this for this one, is to calculate the effect size for the correlation. All right, now the only effect size that we have is the r squared. And so if I calculate an r squared, it's actually very simple and straightforward. An r squared, that's what we're calculating, r squared. And we've been doing r squareds with our t's and our ANOVAs. But with a correlation, it is just take your r, the correlation that we had, and square it. That's why it's called an r squared, actually, is because this, I think it originated with the correlation. So to understand what percent of variance is explained by one variable, how much of the variance of one variable is explained by the other variable, you just square the correlation. Okay, so in our case, it would be negative 0.999 squared. So let me do that calculation here. There it is, and let me just change it to a negative. So it's a negative 0.999,444, etc. And then I'm going to square that. So click squared, and it's 0.999. So it turns out that our r squared is 0.999. Now r squareds are always going to be positive because you're squaring. So how do we interpret this r squared of 0.999? It means that if how much of the variance in the number of mistakes people make can be explained by knowing age, it would be 99.9%. So pretty much almost a straight prediction. If I know your age, I can tell you how many mistakes you're going to make. Now, it's not a realistic result because, again, I just made this data up and I did a small number just to make it simple for us. But that's how we calculate the r squared, our effect size. And again, so let's say we had an effect size of 0.333 instead. Okay, so let's say our correlation ended up with, something not quite as strong as what we got here. So in that case, a 0.33 correlation, r squared, would mean that 33% of how many mistakes people make could be predicted by knowing their age. All right, so that's essentially how the r squared as an effect size helps kind of connect two variables. So one that some of you may be aware of that I often use as an example is SAT scores are correlated with college GPA. That's why a lot of colleges used SAT scores to help do admissions, because it helped somewhat predict how well people would do in college. And that's partly what more selective colleges want to make sure is that they're accepting people who can succeed in college. The correlation between SAT scores and college GPA is 0.3. Okay, so we would consider that a moderate to weak-ish correlation. So it's not a particularly strong correlation. If you calculate the r squared, 0.3 squared is 0.09. What that means is that if we looked at how much variability there is in people's college GPAs, only 9%, because it's 0.09, 9% can be explained by knowing somebody's SAT scores. So that measure of people's aptitudes only predicts about 9% of college GPAs. And so you want to be thinking about, so of course, that sort of makes sense because there's so many other variables that can also impact people's college GPAs. Meaning like, are they working? How many books did they have access to when they were growing up? Did they get to go on vacations and, sort of stimulating experiences? And did they go to better high schools or worse high schools? Are their parents, encouraging them? Are just all sorts of things. Are they hungry? Do they not have safe environments? Do they not have environments that are causing all sorts of health issues? All these things are in that other 91% for sure. Okay. Next question, and it's actually kind of related to some of the following ones. I'm curious, what is the most common mistake students tend to make with correlation or just at this point in the class? Typically, most students do really well in the calculations for correlation because they're a lot simpler than the ones we've done so far. So the one thing I will say is that partly because correlation has these sum of x squared, so you got to make sure you add those right and add those. And then all of these calculations, hopefully by now you're starting to get more comfortable with them. But those are places where people can make mistakes. So, you just want to be, double check your calculations and so on. But other than that, students tend to just breeze through the calculations of the correlation. The problem and the common mistakes students are going to make is the interpretation of the correlation. So correlation simply measures how much two variables appear to relate to each other. It does not, and this is the misinterpretation, it does not explain how they relate to each other. There are multiple ways they can relate to each other. So that's what brings me to many of these other questions, which I think is the common mistakes, is I guess the muddiest things for me are when there are issues with interpretation, restriction of range and outliers, or next one, muddiest thing for me was understanding the difference between correlation and causation. It keeps confusing me. Correlation in comparison to causation. I get stuck sometimes assuming that correlation is in reference to a variable causing the other to change when that could be related for other reasons. And some things that are muddy are the correlation coefficient and causation. Okay, so a phrase that you want to just memorize for the rest of your life, honestly. It is a very important takeaway from this entire class. Correlation does not mean causation. Just that phrase. Correlation does not mean causation. Because two variables appear to be related to each other, statistically, does not mean much. It is just they seem to be connected. Why, we don't know. And the reason why this becomes an issue, and also why it's such a common mistake, even after you're told not to do it, is because our brains are wired to establish cause. So if I hear a rustling in the bushes, like think about when our brain evolved. If I hear a rustling in the bushes and then I get attacked by, a lion or something like that, I need to start to understand that rustling in the bushes essentially predicts, causes in a way, than the lion coming out. So now anytime I see or hear a rustling in the bushes, I'm going to be on alert and ready to run, or I might even start running. That's going to increase my chances of survival. So we need to kind of understand that the world has causal components. And so that lion jumping out can cause me to die or get very injured. And so I need to be aware of that. So our brain is kind of programmed evolutionarily to think in terms of cause. So you're going to have to fight that, because that's just naturally where your brain's going to go. So for example, let's say I said, hey, there's a correlation, a positive correlation between college GPA and study time. That the less people study, the lower their GPA. The more people study, the higher their GPA. Well, what most of you will likely do is then go right to cause. So if I said, well, what should you do to do better in college? And the answer would be, you should study more. That's what the correlation shows you. That is a causal interpretation. You're saying that studying causes you to do better in school. That may not be may not be the case because we don't know yet. The only way in research that we can establish cause typically is when we do experiments. And that's where we have an independent variable and we randomly assign people to conditions. That is, experiments are set up to establish cause. So correlation studies do not establish cause. They just establish links, and then we've got to explore those links more and more and more and more to really try to understand. So why can't we interpret a correlation as causation? So let's say two variables are related. So in our case, we're talking about study time and grades are related, right? They have a reasonably strong or moderate correlation, positive. All right. Essentially think of it as 4 possible reasons, and we don't know which of the 4 are correct. The first is, yes, it could be that studying causes you to do better in school. That is possible, right? So that is A causes B, okay? Studying causes higher grades. But what we call essentially the directionality problem is our second interpretation is that grades could cause studying. It's possible that students who are doing poorly in school start to lose motivation, start to not enjoy school, start to kind of hate school. It makes them feel bad. And so they avoid doing homework. So in that case, it's grades are causing studying times. And so B is causing A. So that's the directionality problem. We don't know if A causes B or B causes A. We just don't know when we do a correlational study. Sometimes we can eliminate one of the directions if one variable is measured first and then the other variable was measured later. Okay, but in this case, they maybe were measured right at the same time. So directionality gives us two of the options, and they're both causal, but they're opposite directions. The third, and this is often a very common one, is what we call the third variable problem. The third variable problem is the fact that sometimes two variables connect to each other, not directly. They go through a third variable. So these are what we call spurious correlations. These are where two variables are correlated to each other, but they're not directly connected. So the common example that statisticians use is the number of shark attacks and the amount of ice cream sold in New York City are positively correlated. It can be shark attacks, it can be drowning deaths, it can be things like that. Those two things have a high positive correlation. But, and again, our brain wants to go causal. It's like thinking ice cream is causing shark attacks. It's like, are the sharks mad that people are eating ice cream? And what does it have to do with New York City? It's because it's not causal, it's through a third variable, which is time of year, season. When it's warmer, people are eating more ice cream. When it's warmer, people are also in the water more, and they're more available to sharks. And so that's why you would get that high positive correlation. That if you took away and you just measured a bunch of, measured shark attacks just during the month of August, let's say, and ice cream sales in New York City, there would be no correlation because we're holding time and temperature constant. So that's an example of a third variable issue. And then the fourth possible explanation is that the correlation you're seeing is just by chance. And in other words, there is no correlation. And this goes back to our whole purpose of our inferential statistics, is that's why we're running inferential statistics, is try to determine, okay, is there a relationship? And then is that relationship statistically significant? Meaning it is unlikely to be happening by chance. So if you get a non-significant finding in a correlation, the best interpretation is that there's no relationship. Because at that point, you have concluded that the relationship you're seeing is likely just due to chance. So it's not real. It's not a real correlation. Okay. So interpreting correlations, the first thing you want to look at once we calculate a correlation is it statistically significant? If it isn't, there's no relationship between the two variables, basically. But if it is significant, then we can start to interpret the direction and the strength and so on. But again, all we can say is that the two variables are related and we can't state cause because we don't know. It could be causal, it could be one direction or the other, or it also could be a third variable issue. So that's why we have to be really concerned about that. Now, in terms of restriction and range and outliers, what we tend to run in there is issues with how especially smaller sample sizes can start to impact the strength of correlations. So for instance, let's first do outliers. So let's say if I'm graphing and just looking at a scatter plot of data here from a study. Okay, so based on this, I might say, yeah, that seems like a pretty good, strong or moderate to strong correlation. Now, again, sometimes it's helpful to draw a line around the data and look at the shape that you get. And this shape is kind of like a thick cigar-ish shape, so that puts us more towards the stronger. So we can kind of think, if it's a straight line, perfect correlation. If it's more like a pencil, then it's a very, very strong. If it's more like a cigar, then it's getting, it's again pretty strong. If it's more like a fat cigar, then it's strong. And then if it's more like a football shape, then we're getting weaker. And if it's more like a rugby ball, then it's even weaker still. And if it's a beach ball, then there's no correlation. So right now we would say this is a moderate to probably a strong positive correlation. Now, what would happen if I ended up with this data point up here? Suddenly, when I have to draw my line around it, I have to include that one. And you see that it weakens the strength of the correlation. So outliers can have this effect. Now, that one might not have a super big effect because we have a fair amount of scores in here. But if we only had like 10 or so, this would drastically change the strength of the correlation. So it can go in that direction, but it can also go like this. So we might end up with a correlation where we just get this, which we would say, again, looks like a zero correlation. But if I ended up gathering one more person and they're way up here, then now this suddenly becomes a pretty strong correlation just due to one person. So that's why we have to be careful. So often when we calculate correlations, it's really important to graph the scatter plot, just so you can take a look, because sometimes you might see a strong correlation and then you look at this graph and you're like, I don't know what's the case here. Could be more like a zero correlation or could be a strong positive correlation, but we don't know at this point. And I would want to gather a lot more data before I really started to interpret it. Okay, so the other thing that happens is that in terms of restriction of range, let's say we have this strong positive correlation. So we got all these data points in our scatter plot. And then we restrict our range. Okay, so what I want to try to do is I want to restrict our range to just high scorers. Okay, so ignore everything to the left of that line. And what you see here is kind of, if we try to draw a line around it, it's a weaker correlation. Okay. It's not quite as strong as what it was before. And if we restricted our range even more, maybe out to here, now when we draw a line around it, it looks pretty much like a no correlation. So this happens when, let's say, I started my study and I just, for whatever reason, happened to only take people who had scores higher than this. Oops. Higher than that point, right? So I just happen to only sample people up there. I would get this correlation and I would conclude that there's no correlation between X and Y. Because looking at that red set of data there, doesn't really look like as much of a relationship. Okay? But if I start to add more and more of the range of scores on X, that's when I then see, hey, it's actually kind of a strong positive correlation. So these are issues that researchers have to be aware of, and so on. So it's just something I want you to understand is that, correlations are important, but they can be easily misinterpreted due to, and again, trying to do data very well, but not necessarily keeping everything into account. So I'll do one last one, which I think is just a fascinating one. Just again, sort of drive home the point that's how careful you need to be with interpreting correlations. And you kind of need to be thinking at multiple levels. So you might get data that, again, has a strong positive correlation. But what I'm going to do is I'm going to separate it into groups here. Color will go orange. Okay. And what this might be is essentially, we'll say maybe college GPA or like semester GPA for college students. And then this might be let's say something like work hours. Okay, So like how many hours they're working during the semester. So this might be more at a traditional university. And so what it clearly looks like when you look at the overall data here is that there's this kind of strong positive correlation that as the number of hours people tend to work outside of school, their GPA goes up. All right, so that might be your interpretation. However, the problem is if you look at each of these groups separately, so this purple group, if you look at that set of scatter plot, that looks like a negative correlation, as does this one, as does this one, and as does that one. Those look like pretty strong negative correlations, which is the opposite. What these different colors might be is first year student, second year students, third year students, and fourth year students. And what you're seeing is that the farther along students are in college, the more they're working. But also, the farther along in college you are, your GPA tends to be higher because students start to get an understanding. Like freshman year for many students is a struggle. And then they get a little better in sophomore year and so on. And so what you could end up with is something that on the surface, if you ignored the conditions of year, which year they are as a student, then you would miss that the correlation is actually negative because you're just looking at the overall data and your conclusion would be that the correlation is positive. So these are the kind of things that you're not going to have to worry about, but they're just things that statisticians do have to be thinking about, and it's partly why correlations are tough to interpret correctly. So you just want to be really careful. The simplest way to kind of approach this idea of, what's the most common mistake people make is correlation does not mean causation. And then just essentially all you know when you get a correlation, if it's statistically significant, those two variables are connected to each other. Positive, as one goes up, the other goes up, and negative, as one goes up, the other goes down. But that's pretty much the limit of it. But people, again, and your brains will want to do this because they're programmed like this, is they'll want to go to a much more meaningful interpretation, which is understandable but incorrect. All right, well, I hope that helps. Hopefully you find the correlation as breezy as most students tend to. And we've got one more statistic left, and it's chi-square. Also pretty straightforward, not a lot of calculations. So we'll get there next week. All right, take care.